Yes, hello everybody. Welcome to today's lecture on classification. Last week we were looking at cluster analysis, which was the task of finding unknown groups in data. Today we are looking at known groups. So basically we know our target. We know that we are looking for the group, let's say transactions that are fraud and transactions that are not fraud, or customers that should be addressed by a marketing campaign, or customers that should not be addressed by this marketing campaign. So basically, we know what we are looking for. We also have examples of customers that reacted to a similar marketing campaign or customers who did not react. What we now want is to learn a model from these examples that helps us to predict for unseen customers if something should happen or not. So the classification is a very important topic. So we will stick 3 lectures on this topic. Today we will in general look what is classification, and we will look at 2 specific classification methods, k-nearest neighbors and decision trees. In the context of decision trees, we will also discuss model overfitting, because kind of the art of learning good classification models is to learn models that are not too specific to the training data, but generalize good to unseen examples. So overfitting would be the case where we learn a model that works very good for the training examples, but fails or does not work that good for unseen examples. We will look at these problems. That's today's lecture. In the next lecture, we will look at model evaluation. These are measures for measuring the performance of our models, and also evaluation setups like cross-validation that we use to estimate these metrics. We'll also look at rule learning, which is another classification technique that learns nice human interpretable rules. So it'll also be part of the next lecture. Then the last lecture looks at naive Bayes, which is a probabilistic classification technique. Afterwards, at support vector machines and artificial neural networks, which are some a bit more advanced classification techniques. And we will finish with looking at hyperparameter selection. We will see that the performance of many of the classification techniques that we cover depends on us setting some parameters of the methods right. And with hyperparameter selection, there are some automated means where we can basically build a workflow where different parameter settings are automatically tested, and then the model that performs best with the best parameters is used as the production model. So that will be the last topic. Good, but let's start. What is classification? So previously unseen records. As read, previously unseen, so basically things that are outside our training set should be assigned a class from a given set of classes. So we know what we want. We want to classify apples into these 2 types of apples. Here we have an unseen apple, and basically the algorithm should learn a model that is very good at assigning unseen instances to these given classes. So approach, given a collection of records, our training set, in our case the 2 buckets with the apples. Each record has some attributes, the color, the weight, the size of the apples, and the class attribute, the type of the apples. Learn a model, so some artifact for the class attribute as a function, for predicting the class attribute as a function of the values from the other attributes. So basically we want to learn something. Input should be the weight and the color of the apple or some other attributes, and the output should be a very good prediction to which of these two classes of apples the apple belongs. There are different variants of the problem. There's binary classification. There's a fraud, no fraud case, true, false. So we're looking at two classes. We'll see that many classification problems that we encounter are binary problems. There are also multi-class classification problems. For instance, if we discretize some value, we have a low category, we have a medium category, and we have a high category. So always when our target attribute has more than two values, we are talking about multi-class classification. There's also multi-label classification as a specific case. There we not only want to predict a single label per record, but we could predict multiple labels. For instance, the interests of a customer not only has one interest, we might want to predict 10 interests, or the number of interests depends on the customer, and our model should only predict an interest if it's rather convinced that the customer has a specific interest. So that's multi-label classification. Let's step a bit back and think what we actually want when we talk about classification, or how we actually use, as humans also, classification in our daily lives. So we look at a picture, we immediately know this is a tree. How do we know? Basically, we have in our brains various classification models that we have learned previously. We apply these models, and they tell us the object with the highest probability that we see on this picture is a tree. How did we come to have these mental models? Basically, as children, we've learned these models from examples. We were walking through a park, we were pointing at things, and our parents told us, tree, 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 playground, ice cream. So by basically having this external training data, we learn models for recognizing things. So basically the process that we did is we look at examples together with a label. Then we compare these examples. We see, okay, for trees, maybe they have a trunk. So all trees that we see here have a trunk. All trees that we see here are somehow green. All trees are big. So from the range of possible features, possible attributes we could use for describing trees, we select some attributes into our mental model. So that's exactly also what computers do. So we, or a learning algorithm, look at positive and negative examples. That's the training data, and we derive a model. Trees are big green plants that have a trunk and no wheels, for instance. Why no wheels? Because we have a negative example of this car, which is also big and green, but not a tree. So the algorithm decides that having no wheels is a relevant attribute given this training data. But of course, models can fail. For instance, down here we have this example of a red tree. There are red trees in the world, and obviously our learned model would misclassify this tree. Why? Because we didn't have red trees in our training data. So in order to learn a better model in this case, we would need better, more training data, or we would need to apply some heuristics that for some reason don't put the attribute green into the model. So kind of a general warning always when we talk about learning classification models, the models are only approximating the examples. The models can only be as good as the examples. If we don't give them the right examples, they can't work. This is especially important because gathering more training data very often costs money. So it's kind of cheap to play around with the hyperparameters of an algorithm. Therefore, data scientists like to do this, but it's expensive to sit down and label manually another 1,000 examples by looking at the picture and writing down what objects are seen in the picture. But in many cases, that's the only thing that helps. So we can only learn something if we have good training data. So our overall classification workflow, we have our training example set, some attributes. One is the class, or also called label attribute. We use a learning algorithm to learn a model from these examples. So basically we said data mining is about finding patterns. So basically the algorithm looks at patterns in the data that correlate with the values of the class label. So stuff like the label is usually no if people have a high income, or the label is usually low if people, I don't know, if attribute 1 has a value yes. Then we use these models to classify unseen records. That's the lower part of the picture. That's called deduction. So we apply the model to fill the question marks to predict labels for unseen records. We not only have a single model here in the picture, we already have a stack of multiple models. This already hints in the direction that we are not only learning one model, but we learn multiple models, then test them, and then use the model that worked best in the test for our production. Yeah, so examples of classification, credit risk assessment. So we want to decide, do we give a customer as a bank another credit or not? Relevant attributes might be age, income, or the debt that he already has. Marketing attributes, previously bought products, browsing behavior, and the attribute could be if we target the customer with in some marketing campaign or not. Spam detection, there we are looking at words that appear in emails. We learn patterns that usually in spam mail such words appear, and in non-spammy mail other combinations of words appear. Or also identifying tumor cells that are an image processing task. So basically we derive features from images. So basically we calculate some values based on patterns in these images, and then we learn a classifier that tells us this picture contains cancer cells or not. Classification techniques, there's a wide range of techniques being used. Here a list of some: nearest neighbor, decision trees, rule learning, naive Bayes, support vector machines, artificial neural networks, deep artificial neural networks, which in addition to just making the classification decision, also try to determine the features that make sense for a specific class. So most of the traditional techniques, they are just about predicting from given attributes, from given features. With these newer, deeper architectures, both steps of the process, the feature engineering as well as the prediction, are covered by a single model. There are also many other classification techniques. This is the selection of techniques that we will, to a certain extent, cover here in the lecture. So let's start with the first one, a very simple one, k nearest neighbors. So example problem, we want to predict the weather in a place where there's no weather station. So this is likely Moosbach, somewhere at the somewhere in the woods. There's no weather station. We want to know, is it likely sunny or cloudy at this place? So idea of K and N is just to look at the closest neighbors of the place. So this place without weather stations in the proximity of this place. There are weather stations that do some prediction. So as prediction for this place without station, we basically have the surrounding stations vote. So we get 3 times sunny, 2 times cloudy, and we conclude that likely the weather at this place is sunny. Very simple, straightforward approach called K nearest neighbors. Has one hyperparameter, the number K, which determines how many neighbors to consider. We also need a proximity metric. So in our case here, it's geographic distance to the place. But if we look at other types of data, customers or a credit card transaction, we need to define a different proximity metric. We discussed this last time in the lecture on cluster analysis, how the proximity metrics depend on the data we are looking at. So a bit more abstract. So K nearest neighbor classification requires 3 things. Our training data, a stored set of records, a distance measure, and the hyperparameter value K. Approach, we compute the distance to each training record. We identify the closest neighbors. We have these neighbors vote, just with straight votes, or we can even weight their votes depending on the distance to the point. So apply weighted voting. Some examples, so we see the influence of the hyperparameter K. If we have K equal 1, the result can be strongly influenced by noise points. So we don't know if this 1 minus sign that's next to our cross, if this is a real good point, or if it's just a noise point that happens to be in the data. So there's a tendency to use larger K values so that single noise points don't influence our classifications. 2 might be an option, 3 might be an option. Of course, we see things get tricky here already because there's this close point and the 2 further away neighbors hint into a different direction. So we don't know if 3 is a good selection here for this parameter. There are arguments in both directions. That's a general case that we very often see in classification situations. We have to set a parameter and we don't know how. Approach here, so if we set it too small, single noise points can influence our classification decision. If we set it too large, some more remote points might have a too strong influence. Approach here is basically just to test. So we'll discuss this next time. We split our data in training and test data. We use the test data together with different parameter settings and then choose a parameter that works best. So there's a section on hyperparameter selection at the end of the 3rd lecture where we'll go into details about the setups that we are using for estimating good parameters. But rule of thumb for K and N, test K values between 1 and 20 and see what happens. So summary about K nearest neighbors classification. It often works quite good. So for instance, for OCR, it's a method that kind of often outperforms even much more complex classification methods. Problem is a bit that it's very slow, K and N, because what basically happens in the background is that all examples need to be checked against the instance to be classified. So if we have several thousand examples, let's be the examples being images, several thousand pixel-wise comparisons of the images need to take place at runtime, and this is very slow. So rather use KNN with restricted sets of training examples. Also, the results, of course, strongly depend on choosing a good proximity measure, all the things that we have said in the last lecture about proximity measures apply. And last point, KNN can handle decision boundaries that are not parallel to the axis. An example here, these are the decision boundaries of a K1 classifier. So basically, the classifier always looks at the closest point in the neighborhood, and depending on the distribution of points, we get these areas. If an unseen example falls in these areas, it gets classified accordingly to the point. We will see in a second that for decision trees, these decision boundaries are always parallel to the axis. So that's one advantage of KNN, that we have this flexibility here. How do we apply KNN classification in RapidMiner and Python? So in RapidMiner, we just have a KNN operator. We retrieve some training data. We might need to normalize the training data. We said the last time, never apply similarity metrics, for instance, to numeric data that has different ranges. This was our 1000 versus 2 example. So the 1000 attribute strongly dominated the 2 attribute. So we normalize our training data. We then have this KNN operator. We load some unseen examples. We apply the same pre-processing, and we then apply the model, the KNN classifier, and we get some classification results. Parameters are the number of neighbors to consider, K, if we want to use weighted voting as well as a similarity metric. Similar in Python, we have a KNN classifier where the n neighbors are the hyperparameter for setting the number of neighbors. We fit the estimator to some training data and labels using the fit function, and we can use it for predicting labels using the predict function afterwards. In Python, we get an array with the predicted labels. In RapidMiner, we can have the predictions be added to the data set. So here we have one data set, kind of one of the standard machine learning example data sets. If some people go to play golf, depending on the weather. So we have the label play here. That's the first green column. Next to it, after we have applied KNN, are the predictions together with the confidence of the algorithm. How are these confidences calculated? They are calculated depending on the labels of the neighbors together with the distance to the point. So we see, for instance, the first 2 predictions are correct. Then the fourth prediction is wrong, but also the confidence values, they are close to 0.5. So the algorithm indicates that it wasn't too sure about its classification decision. Then things also work out nicely. Number 13 is a problematic case. There the algorithm predicts something wrong, and it's extremely sure that the wrong value is correct. So the confidence of yes is 0.83. So this will be a case where it fails, and it will be hard to improve the classifier. We are always talking about we are learning a model. Actually, KNN is not learning. This not learning can be termed as lazy learning, because actually what we do is we store the examples, and at runtime we search through these examples and then select the neighbors and have them predict. So this is called lazy learning. There's no explicit model learned. It's just the example data is used at runtime. So a single goal here is to be good at classifying unseen instances, and KNN can be good at doing this. The opposite of lazy learning is eager learning, where we have two goals. We want to be good at classifying, and we also want to learn something about the application domain. So we want to understand the patterns of the application domain. So we really want to generate an explicit model that to a certain extent is also human interpretable. So basically, if we use a model for saying this guy gets a bank credit and the other person doesn't get a bank credit, we want to be able to explain our decisions afterwards. This is called eager learning, and the next two classification techniques that we will look at, decision tree learning and rule learning, are examples of eager learning techniques where we learn a model that can also be interpreted to a certain extent by humans. So what is a decision tree? Basically, a decision tree encodes a decision into a sequence of single attribute splits, single attributes tests. So for instance, in this decision tree, we first look at the refund attribute. If the refund attribute has a value yes, we directly classify the instance into the category no. If the refund attribute has a value no, we look at a different attribute, the marital status. So there are attribute tests that show us that define how we should branch in the tree, and there are leaf nodes which are our classification decision. So concrete example for this, we always start at the root node. We have a record that we want to classify. We first look at the refund attribute. We see value no. Then we look at the marital status attribute. We see the value married. We end up in one of these leaf nodes, and we assign the label cheat equals no. So straightforward procedure, step by step, we go through the tree. Coming back to decision boundaries of these decision trees are always parallel to the axis, because we always only look at a single attribute at a time. So if we look at this tree here on the side, we first look at x, decide if check if x is larger or smaller than 0.43. This divides the decision space into two regions, and then for both regions we do different things. We look at the variable y, and then depending on our first decision, either compare y with 0.47 or 0.33. So basically, step by step, we divide the space into areas. The shape of these areas is always parallel to the axis. So now, interesting question, how do we learn such trees from training data? So basically, we have our training data. Together with a label, we want to end up with one of these trees. How can we do this? So in general, finding an optimal decision tree is an NP-hard problem. So we can't solve this, but people have proposed various heuristics for inducing rather good trees. basic idea of these heuristics is that we use a greedy top-down approach. So we always locally check what is the best attribute split, then we apply the split, then we have 2 new data sets, then for these data sets we again check what's the best split, and by doing this in a recursive top-down fashion we build our trees. So there are various algorithms for this. Most of them are variations of Hunt's algorithm, and we will look at an example of this, how this algorithm works. So basic idea, we look at our set of records, so attributes plus labels. Using these records, the set D, we either generate a leaf node or we generate an attribute test node. If all examples in our set have the same label, we generate a leaf node, and the label of this leaf node is the class of all these training records. If that's a normal case, our set of record contains different labels, we basically go through all possible splits. So we look at all attributes that exist, we look at all attribute values and check which split would produce for this set of records the cleanest subbuckets. So basically how we could split the set of records into 2 sets so that the distribution of the labels in these new sets is as pure as possible. So we choose a test resulting in the highest purity. Then we have 2 new sets, again with a mixture of labels. Again, we test all possible splits for these 2 sets. For each set, we again select the test that increases the purity of the sets the most. Concrete example for this. So we start with all our training records. That's the 10 records we see. We go through all possible splits. We check, okay, refund, what values do we have there? Yes and no. We see how clean are the sub-buckets if we would split on refund. We compare this to how clean the sub-buckets would be if we would split on marital status. We look at taxable income. This is a bit more tricky attribute because it's a continuous attribute. We will discuss how we find a good splitting boundary for continuous attributes in a minute, but also there we test different splitting boundaries and then compare all these splits and come to the conclusion that for these records, splitting on refund gives us the cleanest sub-buckets. For instance, we have this 1 bucket refund yes. All these records are cheat no records, so we already finished with these records. Next, we look at the remaining 7 records. So these are these records. Again, we check all possible splits. We look if we would split by marital status married, by marital status single, by divorced, again by different boundaries on the income, and we come to the conclusion that splitting into married versus other attribute values gives us the cleanest subbuckets. We do it again, now only with 4 records left, the ones that have refund no and marital status single or divorced. For these people, it depends on the income, so people with a low income don't cheat and people with a higher income do cheat. We apply another attribute test. Now we are only left with completely clean subbuckets and we finish. We have learned this decision tree that covers all our training examples. So for doing this, we have various things to take into consideration. We could apply different types of splits, and how we split also depends on the data type of the attribute. So we could, on the one hand side, always have two sub-buckets, or we could do a multi-way split and have multiple sub-buckets, 3, 4, 5, 100. Also, for nominal values, it's easy, but for ordinal attributes, we might need to keep the order of the attributes when we do the splitting. For continuous attributes, we either need to discretize or calculate the splitting boundary. That's the one aspect. The other aspect is how do we actually calculate this purity of the resulting sub-buckets. There are multiple measures that we can apply for this. That's how we do the splitting. The second question, which goes into the direction of overfitting, is it really smart to learn complete deep trees that perfectly cover all training examples, or does it make sense to learn a bit shallower trees that might generalize better to unseen examples? This is something we will also look at in detail in a minute. So let's start with the different ways how we could construct our trees, how we could split, and how we choose the best split. So as I said, the ways how we split depend on the data type of the attribute. So for nominal attributes, we could either have a multi-way split, each value of the attribute gets a sub-bucket, or we could have a binary split where we would somehow arrange the values into two groups. We are free in how we want to arrange the values. Differently with ordinal attributes, if we want to do a binary split, here we need to keep the order of the values, so it makes, for size, it makes sense to group small and medium into one bucket and large in the other one, or medium and large in one bucket and small in the other one. Combining small and large does not make sense. So something to consider when defining our splits. For continuous attributes, we have two possibilities. Either we discretize them. This means we turn them into nominal attributes. So basically, we define buckets and saying, for instance, all values between 10,000 and 25,000 fall into one bucket. All values between 25 and 50 are another bucket. Depending on which value the attribute has, we replace the actual detailed value with the name of the bucket. That's discretization. We have two possibilities of doing this. We'll look at them in a second. The second approach is binarizing the attribute, which normally is sufficient in practice, and we will see how we use our purity measures for finding a suitable decision boundary in a second, in 2 seconds. Let's start with the discretization example. So we have these values. We could either, for putting them into buckets, we could either apply equal interval binning. So basically, we take the value range. We have equal width buckets. Here, 0 to 10, 10 to 20, or 20 to 30, or as far as we go. And we basically assign the values to these buckets. Equal frequency binning is the alternative, that we look at the distribution of the values and we have flexible bucket boundaries, and we set these boundaries in a way that the same amount of examples ends up in each bucket. These are the two automated approaches. Sometimes it also makes sense if we have some knowledge about the semantics of the attribute to use user-defined binning boundaries. For instance, we have the age of a person, and we think we want to learn, want to do eager learning, so a model that we can interpret. So it might make sense to define the boundary as kind of 18 and younger, or 65, older and younger. So we want kind of young people, people in working age, and likely retired people. So that's the third option, user-provided discretization boundaries. But no matter which approach we use, we replace the continuous value with a nominal one, and then can apply the normal things we do for nominal values. So now the more challenging, the second question, which split is the best one? So we have a data set, we have 20 records, 10 records depend to the one class, 10 records depend to the other class. Now we want to divide them into sub-buckets in a way, by looking at the attributes in a way that the resulting sub-buckets are cleaner, have a higher purity. So we could either split on gender, then we would end up with these sub-buckets, 6-4 versus 4-6. It's not too clean. The examples are still rather mixed in these buckets. We could choose another attribute, the car type, for instance. Then we would end up with 3 buckets, 1, 3, 8, 0. That's a very clean sub-bucket. Kind of all examples in the sub-bucket are of class 0. The third sub-bucket is 0, 7, which is also kind of clean. So this might be better than the first approach. Or we could split by customer ID. This gives us many buckets. For each customer, we are getting 1 bucket. These buckets are also extremely clean because only 1 example in each bucket, but that's also not what we want. This hints again into the direction of overfitting. So if we split by customer ID, we have unseen records with different customer IDs. Our model won't be able to predict anything, so that's clearly not what we want. That's a clearly overfitted model to the training data. So which of the splits is best? We don't know, and basically we need to apply a purity measure, so some metric which we calculate from the distribution of the examples in these sub-buckets, and this metric should tell us how the purity, how homogeneous or non-homogeneous the examples are. So a bucket with equal distribution of C0 and C1 would be absolutely non-homogeneous, and a one with 9-1 would be rather homogeneous, 10-0 would be absolutely homogeneous, only one class. The measures that we could use or that are often used in the context of learning decision trees are Gini and entropy. We'll look at both and also how we use them. So the idea is that no matter where we are in the tree, we have the purity of the parent node, so the node before splitting. We have different options how we split. For each of these options, we calculate the purity of the resulting sub-buckets. There we have to take into consideration that the sub-buckets can have different sizes. So basically, we need to weight the resulting purity values according to the size of the sub-buckets. Then we have the purity after splitting, and basically we calculate the purity gain and choose the split that has the highest purity gain. That's our idea. Concrete example. So purity before splitting, that's our P at the top. We have two alternative splits, split on income or split on marital status. Applying these splits gives us sub-buckets. We can calculate the purity measure for each of these sub-buckets. Then for each split, that's the purity measure M1 and M2, for instance, for split A. Then we weight these values with the size of the sub-buckets, get a combined purity of both resulting sub-buckets. We subtract this from the original purity, and we look where we get the lowest value. We do this procedure for all possible splits. So that's the approach. Now a bit about the definition of these measures. So with Gini, it's just a defined measure with information and information gain. People like to interpret the measure, but actually there isn't too much to interpret. It's basically, it's a measure, so our goal is if the things are completely clean, we want a low value, and if they are impure, we want a high value. This is what happens here. So the Gini is defined as 1 minus the relative frequency of the different classes in the resulting set, and these relative frequencies are squared. So we basically want to put more weight at distinct relative frequencies. Yeah, so basically for all resulting sub-buckets, we take the relative frequency of all classes, we square it, we sum up these values, and we subtract it from 1. On the next slide, we have an example of this calculation, but you already see here the results. If a bucket is extremely clean, we get a low Gini value of 0. If the bucket is completely inhomogeneous, we get a high Gini value of 0.5. Some concrete calculations. Basically, the relative frequency of class 0 of class 1 would be 0. So 0 times class 1 divided by the number of examples in this bucket. The relative frequency of class 2 would be 1. So 6 records having class 2 out of the 6 records in this bucket. We square both of these values. We subtract them from 1, and we end up with a Gini value of 0, saying that we have a completely clean bucket. Some more examples. You see, if the buckets get less clean, the Gini value increases. Now we need this weighting. So we have different sub-buckets. They have different sizes. So for calculating the Gini of the complete split, we weight the Ginis of the separate sub-buckets according to their size. So take the Ginis, weight them according to the size, and then add up all these weighted values. This gives us the Gini of the complete split that we use for deciding which split to prefer, and this also allows us to compare two-way splits with three or multi-way splits, because basically we take the size of the resulting subsets into account. Again, an example, one split yes, no. At node 1, we would have 5 examples of class 1, 2 examples of class 2, so overall size of 7, and this would result into a Gini of 0.408. Second bucket is 5 examples, so it's slightly smaller, gives us a Gini of 0.32. We weight both Ginis with the size of the buckets, so that is 7/12 and 5/12 on the other side, and we get our final purity gain, which basically is the purity of the parents, the 0.5, minus the weighted average of the purity of the children. This is what we do for nominal and ordinal attributes. If we do a multi-way split, we just calculate one Gini. If we have different, if we want to do a two-way split and we have multiple value, we do different combinations of the values. Here, sports car combined with luxury versus family car, or sports versus family car and luxury. We calculate the Ginis for all these splits, and we would conclude that the three-way split is the best one. If we want to do two-way splitting, likely the first one is the better one. Now the bit more tricky part with continuous attributes. So we now want to use the Gini to learn the ideal splitting boundary for a continuous attribute. So we want to end up with this 80,000. That's a good idea to split in our initial tree on 80,000 as income boundary and not 87,000, for example. So what do we do here? We take all existing values in the data set, in the training set, so all income values, and we sort them by their value. So income 60,000, 70,000, 75, 80,000, and so on. So all the values that we find in the data set. Then we put boundaries in the middle between all existing values. So that's between 60 and 70, we put 65 as potential splitting boundary. Between 70 and 75, we put 72 as potential splitting boundary. So we have that's the second row, the possible split connections, split positions, and now we once scan over the data set and basically calculate the Gini for each of the possible split positions. So initial split position, even below our initial value of 60, 55, just randomly taken. We could also have taken 40. Basically, we check, we count, we calculate the Gini for how many of our examples have an income value above 55 and how many do have an income value below 55. We count through our examples and we end up with none of our examples has such a low income value. So no matter if it's the example is a class yes or a class no example, none has this value. All examples, all 10 examples have higher income values than 55. These are again our counts. From these counts, we can just calculate the Gini as we did before, and we end up with a Gini of 0.42. Now we move to the next possible split boundary. There we have one example that has a value below the 65. That's the one example with a 60. So our distribution of the examples over the classes changes. We again calculate the Gini, which is now 0.4, getting down. We go to the next split boundary. Now we have two class no examples that have a value below 72. We again calculate the Gini and get values. You see, if we do this, the values decrease. We find the minimum value to be 0.3 if we use the split boundary of 97. So rather compute intensive, but gives us the best split position. So I said we can not only use Gini for splitting, we can also use other purity measures, for instance, entropy. So entropy is measure from information theory, so we can try to interpret it, or we can just use it. That's how we apply it here. So we take the formula of entropy, which is minus the sum over all classes, the relative probability again of a certain class in a sub-bucket multiplied with the logarithm of the base 2 of this relative frequency. That's the entropy. Our goal is we want low values if the distribution, the buckets are clean. We want high values if the buckets are non-homogeneous. And this is what's happening. We can look at some examples. So completely clean sub-buckets give us an entropy of 0. If we are moving towards more less homogeneous sub-buckets, the entropy raises. Again, we need to weight the values based on the size of the buckets. So the information gain of a split is the entropy of the parent node minus the weighted average of the entropies of the resulting subnodes. So same approach as we used together with Gini, now just with a bit different terminology and the entropy metric as a purity metric. With using entropy, there's an additional measure called gain ratio. We've seen this example of if we would split by the customer ID. So if we would get really lots of sub-buckets, these sub-buckets would obviously be very clean, because one record per bucket. So basically, people which would be overfitting, which we discuss in a second. So people wanted to normalize this information gain by the purity of the resulting sub-buckets, and this is the idea of this gain ratio measure. So basically, we calculate the information gain of the split, and then we divide this by the entropy of the split itself. This entropy of the split itself, it's called split info. That's the formula for it. I don't go into an example, but basically the idea is if we have many sub-buckets and a kind of homogeneous distribution of the examples over these sub-buckets, then we want a high split info value and basically put a penalty on our gain value. one way to prevent overfitting, which we will discuss now. So what's the problem with overfitting? We can learn models that work perfectly on our training data, but which fail in the general case on unseen data. And we said at the beginning, our overall goal is to learn something that works on unseen data. So for a marketing campaign, we have asked 100 customers if they would buy something. Now from these 100 labeled records, we want to learn something for unseen customers, for the other customers. We don't care how good the algorithm works for the 100 customers. We want to learn something about unseen different customers. So yeah, we already had this example of the red tree. So we've learned a model. The model, based on the training data, decided that green is a good attribute. Now we have an unseen example, red, of a red tree. The model fails to correctly classify this unseen example. So now we need to discuss, need to think about things, how we could prevent a model from overfitting, from becoming too specific to the training data that it doesn't work for unseen instances. So our goal is to find a good compromise between the specificness of the model. So we want to learn these attributes. So it doesn't help us if we just check, have a very simple model, just check if the thing is big, or if it's big, we say it's a tree. This model would make too many errors. So the model needs to stay somehow specific for being able to distinguish between, let's say, trees and houses. But we also don't want to become over-specific, overfit, that we can't deal with these reddish trees or some other trees which we haven't seen beforehand, so we don't know which attributes, values we will encounter. So another example for overfitting, now from the finance domain. So we want to decide if we give these 4 people additional credit or not. We know their name, their income, their job status, and how many credits they have already gotten. And we it's our training examples, so we know their rating plus or minus. So we could learn a tree saying if somebody would have a debt higher than 5,000 already, we don't give him additional data. This very small, very shallow decision tree perfectly fits our training data. We don't make any errors. All 6 examples are correctly classified. That's one possibility. We could also learn this tree. We could say if somebody is called John, we give him credit, or if somebody is called Alice, we also give her credit. If people have different names, we don't give them credit. Intuitively, we know that this tree doesn't make sense at all. But if we look at the training data, the tree also fits the training data perfectly. So we need some additional input for deciding which of these trees potentially makes more sense, potentially generalizes better. And for this decision, we go back to the middle age. That's our decision, which one to prefer. And for doing the decision, we go back to the Middle Ages and apply something called Occam's razor. So this guy was a monk in the 1200, living 1200 to 1300, and basically his statement, Occam's razor, is if you have 2 models that equally good explain some phenomenon, prefer the simpler one. Very straightforward, a heuristic. which empirically show to work quite nice, and in our case would hint towards using the depth over 5,000 model, because it's a smaller decision tree. We only have one node, not two nodes, two split nodes. That's simpler, therefore we should prefer this model. Interestingly, Occam's razor is a very good approach for preventing overfitting, or to recognizing, for selecting models that likely overfit less, because what happens if a model overfits? So here we have the error rate of a model, how good it is at classifying unseen instances. And we have the number of nodes, so the size, the complexity of the model. And what usually happens if we add additional nodes, if we make the model more complex, is that it works better on the training data. So basically, we look at the training data, and for each specific pattern in the training data, we add nodes to our model. To a certain degree, adding these nodes to the model also helps for the general case, helps for unseen records, helps for our test set. That's the blue line. So at the beginning, the blue line goes down, but at some point, it starts growing again. And this is the point where our model has gotten too complex and now has started to overfit the training data. So it didn't model general patterns that exist in all data. It started to model specific outliers that only exist in the training data, or specific patterns that only exist in the training data but not in the general data. Therefore, it's got better on training but worse on testing. So symptoms of overfitted trees, they are very deep, they have many branches, and they don't work so good on unseen test data. Typical causes: too little training data, so we don't show enough examples. If we don't show a red tree, there's no chance that the model learns that there are red trees. Also, noise in the training data could be a problem. We will see this in a second. And also allowing too flexible models. This is something that we will see when we look at neural networks and deep neural networks later. So if we have a really flexible model that can easily adapt to very specific patterns in the training data, these flexible models have a high tendency to overfit the training data. So let's look at an example of these noise points, these outliers messing up our models. So here we have some points, circles and squares. We have a decision tree that splits the space into decision areas. So first we look at the x value is bigger or larger than 2. Then we do specific things for these two areas. And in the left area, there's one outlier. And if you look at the details of the tree, this single outlier is modeled with a complete subtree. So basically what happens, the model first checks if the x value is below 2, and then it checks if the x value is below 2.5, then it goes for square, or if it's higher, it checks again. If it's above 0.6, then it goes for square, and otherwise it goes for circle, so it models this specific outlier. So very complex tree has become complex because of a single noise point in the data set, and as we allowed the tree to become as large as it wants. So likely the lower tree doesn't perform that good on the training data. It makes one error on the training data, it's not able to correctly classify this one circle, but likely it works, according to Occam's razor, it likely works better on unseen instances. Let's look at a bit bigger examples. There's also the opposite of overfitting, which is underfitting. So if we show the model not enough training examples, or if we just have a too simple model, so here we have a decision tree with 4 nodes, and the learning algorithm can't put these 4 nodes in a way that they are really able to model all relevant patterns in this rather large data set that we see here. So basically, given that it can only set 4 nodes, the algorithm would choose the ideal splits for these 4 nodes, and it would end up with a model that is rather bad at classifying training examples and rather bad at classifying unseen test examples. Because just the model is too simple, it's bad on training and it's bad on testing. That's underfitting. The alternative, if we give the model too much freedom, we allow it to grow too much, we get, for instance, this decision tree with 50 nodes that we see in the second picture. We already see that it models outliers, so there are these strange regions which model single plus signs. So again, this model is overfitted. What we want is the ideal model, so we want the size of the model to be in a way that kind of the training and test error are low, but still we don't have a high difference between the training and the test error. So ideal point is this ni value. Training and test error are rather low but similar. What can we do to reach this ni value? We can add more training data. This is costly, so basically we annotate more pictures. At some point we will get a picture of the red tree. We add this picture to our training set, and our training set and our model will perform better. So adding more training data, we say that a model is underrepresentative if basically the the training error decreases if we add more, allow more model complexity, but the testing error increases. So basically this is the case here. The model is overfitting to the training data because the training data is underrepresentative. We don't have the red tree in our training data. We add a significant amount of additional training data, which usually narrows the gap between the training error and the test error, because as there are now more examples, the algorithm has a more solid foundation for setting these decisions. The tendency of modeling using the freedom of the model, the nodes for modeling single outliers is lower, because in the correct decision areas, basically there are more examples, and as the model tries to cover as many examples correctly as possible, it will use its freedom, it will use its split nodes rather to cover the dense areas than to cover single outlying nodes. So something that always helps is increasing the training data. But problem is increasing the training data, it's expensive. Therefore, people have thought about cheaper heuristics that might also solve the problem. I say might. For instance, pre-pruning. Here the idea is that by applying Occam's razor, we don't learn deep trees that potentially, just because they are deep, because they are very detailed, they might overfit the training data. We basically stop the learning process early, have shallower trees that are not as good as the training data, but which might work better on the test data. Again, in the next lecture, we will look at the setups that we use for estimating what works good on test and training and how we do these splits. But general idea, pre-pruning, normally we would stop if all instances in a sub-bucket belong to the same class, or all instances in the sub-bucket have the same attribute values. With early stopping, pre-pruning, we use a user-provided threshold. For instance, we say we generally stop splitting nodes that only contain 4 instances. Again, this splitting boundary, this minimal leaf size, is a hyperparameter, something that we can experimentally set and see which of these thresholds works best. Or also we could stop early if splitting would only improve our impurity measure slightly. So in the examples, our purity gain was usually 0.2 or 0.15. We could, for instance, say that if we would split and the purity gain would be below 0.01, then we don't split. So also an early stopping criteria. That's pre-pruning, heuristic based on Occam's razor. Alternative is post-pruning. Here the idea is that we first learn the complete tree. So we learn a tree as deep as it wants to grow until it perfectly fits all training examples. Then we, step by step, bottom up, remove parts of the tree and see if the simpler tree works better on a validation set. So we'll come, when we talk about hyperparameter selection, we will come to how we split our training data into actual training set, a validation set that we can use for pruning, for instance, or for generally setting hyperparameters, and in a test set that we use for finally evaluating our model. So here the idea is we use a validation set, we keep some examples aside, we learn a deep tree, then we test this deep tree on the examples that we have put aside, we remove parts of the tree, and we see if it works better on the examples that we have put aside. If this is the case, we estimate that our tree will work as the prune tree, the more general tree will work better for the general case, as we think that these really deep nodes, again, model outlier, model specific patterns that exist in our training data but don't exist in our validation set. 2 ways of post-pruning these trees. We could do subtree replacement. So we say, as we've seen in the example, we say there's this outlier point, the whole subtree just models this outlying point, so we just remove it. That's here, this complete subtree is removed, and we just, if we reach this point in the decision tree, we just classify the thing to be class 0. Alternative is subtree raising. Here the idea is that we look how many training examples go down which passes, basically end up in which of the final nodes. And we look at a subtree, and we take the most frequently used branch. So if, let's say, from one subtree, there are 25 examples going into the subtree, 20 examples end up in one branch, 2 in the other branch, 3 in the third branch. We basically say we remove the 2 branches where there aren't that many examples and just keep the one big one because we think that this one generalizes better. That's post-pruning. You see, people in machine learning are creative. There are also other ideas. One idea is using ensembles of multiple classifiers. That's kind of wisdom of the crowds applied to classification. So one classifier could overfit too much on some specific patterns in the training data. So why not learn 10 decision trees, or why not learn 100 decision trees and have them vote on the final decision? That's the idea of using ensembles of base learners. So we take our training data, we learn 4 models in this case, or in realistic cases, hundreds of models, and then we have them vote. Different models can focus on different aspects. Different models likely don't overfit the data in the same way if we introduce some randomness into the learning process. And that's the idea of one variation of decision trees, which are called random forest, and it's quite widely used in practical projects. So we use an ensemble of a large number of decision trees, usually between 50 and 200 maybe. We have them vote for the final decision, and the interesting or a bit surprising aspect is that we don't learn all these decision trees from all training data that we have, but we randomly remove parts of the training data for learning specific trees. So basically, at each node, at each decision for a random forest, we don't check all possible splits, all attributes, but we randomly remove some attributes. So for the second split, we only look at marital status and income. We don't look at refund. Randomly, we remove some attributes. As these attributes don't exist when we learn the specific split, the learner will focus on a different aspect, because it can only choose between these 2 attributes, not the third one, so we get different trees. We can do the same also for the training examples. So for learning specific trees, we don't use all training data, but only subsets of the training data, random subsets. So the one tree gets this 80% of the training data, the other tree gets some other 80% of the training data. Again, we will end up with slightly different trees, which we then can have do voting. Maybe we can also weight their votes by the confidence, how sure they are about their classifications, and then we end up at some final classification. And interestingly, empirically, these classifications usually generalize better than using single trees. So often when we compare a single tree to a random forest, if we evaluate with F1, which is a measure that we'll discuss in the next lecture, very often we get between 2 and 5% better F1s if we use random forests instead of single decision trees. Of course, one aspect of decision trees is the interpretability. So if we have a single tree, we can look at it as a human and say, this is the most important attribute, and then we did this and that. If we have a forest with 100 strange trees, it might work better, but we can't interpret it that much. Basically, we can still conclude attribute weights. So this one attribute appears in 95 trees at a rather high position. The other attribute only in 80 trees, and it is slightly lower position. But in general, that's getting rather indirect. So random forests, they work better, but they are less interpretable compared to single decision trees. So now how do we practically do all this stuff? So in RapidMiner, we have a decision tree operator. Again, we load data, we pre-process it, normalize, discretize, whatever is necessary. Then we apply this decision tree learning operator, parameters, gain ratio, Gini, entropy, information gain, whatever we want. Maximal depth, that is pre-pruning. We say we don't want deeper trees than 10. Confidence is if we do splitting, how much gain do we have? Minimal gain, maximal leaf sizes are all pre-pruning parameters that we can set. If there are only 2 examples, in some bucket, don't split it again. In Python, we can do the same. Here it's a decision tree classifier, that's a class. We can set the parameters criterion to Gini, for example. We can restrict the depth of the trees. Again, we use the fit function to learn our decision tree, and then we use the predict function to classify unseen instances using this decision tree. We can visualize our trees. That's a standard visualization in RapidMiner. At the top, that's a visualization that many people use in Python because the visualization code is available. The interesting thing about the second one is a bit more detailed, and it shows you how the training data was used to build this tree. So we started with 100 training examples that were distributed over 3 classes. We had a Gini of 0.66. Then we did one split. We had a complete clean sub-bucket. That's the red one. We had another kind of mixed sub-bucket where 67 examples ended up in, which we did split again, and we end up with 2 buckets which are still not 100% clean. So basically, we likely have set a max step constraint here and didn't allow the tree to grow to its full depth in order to have it to generalize better to unseen examples. So we see what has happened. For random forests, we can do similar things. So there's a random forest operator in RapidMiner where the number of trees is one parameter. Besides, the parameters are rather similar to the decision tree parameter. Same in Python, random forest classifier. N estimators defines the number of trees that we want to learn. Criterion is the purity measure that we use. Max step is again a pre-pruning threshold. Beside of this, straightforward. So to conclude, what are the advantages and disadvantages of decision trees, also including random forests? So basically, they are rather inexpensive compute-wise to construct if we compare them to other classification techniques, especially neural networks. They're also extremely fast as classifying unknown instances because it's just small number of attribute checks and then the instance is classified. They're easy to interpret if they are small by humans, so it's eager learning. We know why the algorithm has decided in a specific way. Also very good, very important, tree-based classifiers do feature selection for us, so we can give the learning algorithm 100 customer properties, and it selects the 3 customer properties that matter for the classification decision. Because it always the best one, the next best one, the third best one, we define a depth threshold of 5, so out of the 100 property, at most for one pass, it can only select 5 properties. So decision trees and random forests are very good at doing feature selection for us. They can work with irrelevant attributes and also with redundant attributes. Their accuracy, which is another performance measure, is comparable to other classification techniques. If we have low dimensional data, low dimensional means up to, let's say, 100 attributes, then they still work. If we have really high dimensional data, like image data or text data, where we look at 5,000 or 10,000 attributes, decision trees usually don't perform well. Disadvantages, they are not optimal, so some other classification techniques that really use optimization might perform slightly better, because trees are learned using some heuristic, so it's not the optimal shape, it's a heuristic shape. And decision trees always look at single attributes, so if your classification decision has interactions between the attributes, you need to look at 3 attributes simultaneously to understand something. Trees won't work. Yes, that's it, and basically you can read all these things in these chapters in our textbook. Thank you.